Okay, why don't we get started here? It's just a few minutes past 8:30. Welcome. This is the Analysis of Categorical Data Continuing Education course here at JSM. My name is Chris Builder. My colleague here is Tom Logan, and we will be the instructors for the course. If by chance you were able to get by that front table out there without picking up a handout, you might want to go back out there and get one of these paper handouts. There's what? I'm sorry? Okay, so a few things. We are recording this continuing education course. If you notice, there's a webcam right in front of me that's capturing live action video of me. Be very careful if you come up here, because I have a cord from my laptop to that webcam there. I don't want you to trip, so be careful. Okay, so the organizers of these continuing education courses ask that all courses begin with a statement of the objectives and also end with a statement of the objectives as well. So let's go ahead and talk about the objectives of this course here today. So the first thing that we're going to do is look at appropriate methods to analyze data in a contingency table. And we're going to be quite simple here. We're going to look at a two-row, two-column table because they are so prevalently used. But also what that's going to do is allow us to get some background into odds ratios. And odds ratios appear throughout categorical data analysis. And so it's good to get a firm grasp of what these odds ratios are actually measuring, so that when we talk about more complex settings in a regression modeling case, you're comfortable with these odds ratios. So speaking of regression models, we're going to be looking at how to state, how to interpret, how to fit logistic regression models, multinomial regression models, proportional odds regression models, Poisson regression models, and even a few that I didn't even mention there. And in many cases, too, we're going to be trying to figure out, well, which variables do I include in one of these regression models? So we're going to be looking at appropriate variable selection methods, such as Bayesian model averaging, to help us do that. Well, also, once we get what we think is a good model, we're going to be looking at ways to evaluate the fit of the model, so we can understand how well does it fit the data. And we'll be focusing on a specific kind of problem that occurs with these categorical response models, sometimes called overdispersion. Simply what that means is that the variation in your data is more than what you would expect given a particular model. And so we'll look at ways to identify overdispersion when that happens, and also how to solve it. And lastly, we want you all to be comfortable with using R to analyze categorical data. There are going to be many, many, many R examples throughout, and we want you to be able to come out of here with a good sense of how to use R to analyze this type of data. Okay, so on slide 3 here, we have the beginning of our table contents. I'm not going to go through that here. Rather, this is a reference for you to use here today if you want to see where we are going in this course, and also after today when you may want to review these handouts. But I do want to mention one organizational structure of these handouts. And at the very top of our handouts, you're always going to see the section that we're in. So right now we're in the introduction. And also you're going to see the subsection that we're in. So right now we're in the table of contents. So I think this is a handy tool when you have 210 slides to try to figure out where you're at. Now, our continuing education course here is based upon a book that Tom and I wrote recently called Analysis of Categorical Data with R. This was published by CRC Press. And while you don't have to purchase a copy of the book, I do want to give you a little tip, though, that if you did want to purchase it at the JSM Expo, it is 50% off right now in celebration of this continuing education course. So you're welcome to go down there during lunchtime to pick up a copy. But anyway, the reason why I mention this is that our course is based upon the material that we put together for this book, and you know, it has over 500 pages in it, and as you might expect, we cannot talk about everything that's in that book. So if you want to have more depth to some of our explanations that we have here today, or if there's a topic that you're interested in that we didn't cover here today, you know, take a look at the book. With this book, we constructed a website at chrisbaylor.com/categorical that has over 80 R programs with over a combined 11,000 lines of code in it. It has over 35 hours of instructional videos. There's even lecture notes, projects, and tests from when we actually teach a corresponding course on categorical data analysis at our respective universities. This website's available to anyone, whether they have the book or not. Now, a few additional items. Excuse me?
The slide you just put up,
Sure. Would you like me to be in the picture? It's like I'm on The Price is Right.
Your book is different from the Cresti book, maybe because you have a all-based programs in there?
Well, our book is different from Agresti. I mean, Agresti's a fine book, but you know, we felt as though there was some aspects of it that could be improved, and so we actually embed our R code and programs right into the text, and that's one of the things he does not.
Who's the publisher?
This is CRC Press. Okay. So some additional items before we get going here. Of course, the course is in session from 8:30 to 5 o'clock. In terms of the breaks, we'll have one at 10:15. Our lunch will be an hour and a half. It starts at 12:30. And also, we will break at 3:15. I've also set up a corresponding web page, chrisbaylor.com/JSM, for this continuing education course. And as you might remember from seeing in the abstract, as I mentioned briefly earlier, we are recording this short course here. We are capturing everything that's up on the screen there, including any of my annotations. We're recording live action video of me, and I hope to be able to post that to our website when I get back from JSM. So I would imagine by the end of the week it will be out there. And I will post the recording out there for about a month, and then I'll take it down. And so in the meantime, or after it's posted, you're welcome to download it. It'll probably be about 500 meg or 750 meg in total. Also on this web page, we have all of our links to all of our R programs that we referenced from the book that we will be talking about here today. And as I mentioned earlier, for those of you who were here a few minutes before our course started, our handouts are available from there if you want to take electronic notes on them. With respect to these handouts then, you know, all of our slides that we will be presenting here today are in this packet. A little organizational structural note is that whenever we have a data example, you'll see towards the top of that slide, or multiple slides, if it goes over multiple slides, you'll see simply example, the name of the example, and also the corresponding R programs that we will be using for that particular example. Again, that's there to help you out, you know, especially after this course. Also, towards the end of these handouts, you will notice that there is an index that has all of, an R index, I should say, that has all of our programs that we reference, important functions that we use, important packages that we use, and again, this is here to help you, especially after today, when you go back and look at these handouts. Now, there will be, as I said, a lot of R examples that we talk about here today. I recommend that you don't actually try to execute the R examples yourself while we're going through this course. We don't see this as a workshop. We see this more as a course, and we have a lot of material to cover, so we chose to take this approach rather than have you interactively execute some of the stuff that we'll be talking about. If, however, that you choose to go ahead and try to execute some of these R programs as we're going through them, we ask you to please postpone questions about why your R program is not running until break time, and we'll be happy to answer those questions. And then lastly, as Tom and I were putting together our slides for the course, we ended up deciding to cut some out just to make sure that we can finish on time. But since we already have made the slides up anyway, we thought, well, why don't we just go ahead and post them to our website, and you're welcome to download them there. And lastly, all these slides, we had to turn them in to the organizers of these continuing education courses in early July. And as we were continuing our preparations for this course, we came across a few places where we thought, well, it would be nice if we made a small change here and there. And so whenever you see bold blue text on the screen, that corresponds to something that's not in the handouts, something that we've made a change to after we turned in the handouts and the handouts were printed. There's not many places where that occurs, but there are a few. Okay. So, are there any questions before we get going here? Yes?
I'm in a situation where I need to take survey concepts like stratum, cluster, and sign effects and apply them in a context where the customer has a lot of proportions. Is your framework going to cover?
Are you talking about a complex survey sampling setting? We are not going to do complex survey sampling here, but you will find a section in Chapter 6 of our book that does. Okay? Any other questions? Okay, so we're going to begin in a simple setting that I would expect most of you have seen before, and that is we have a binary response, and it's summarized in a 2x2 contingency table, meaning 2 rows and 2 columns. And again, the reason why we're focusing on this is, first of all, we got to begin someplace, and we want to begin a place where it's going to be familiar to a number of individuals. But also, we're going to really focus on odds ratios and helping to understand what these odds ratios are measuring. So let's begin by taking a look at 2 data examples that are 2x2 contingency tables. This first example here is maybe my favorite contingency table, if one can have a favorite contingency table. But then again, that's why I wrote a book on categorical data analysis, because I like this stuff. And this is regarding Larry Bird. Larry Bird is a famous basketball player from the 1980s and early 1990s. Thought of as one of the best basketball players ever. And what we have here is a table summarizing his free throw attempts during over 2 different seasons in the early 80s. And for those of you who are not familiar with basketball, basically with free throw shooting, it's a type of shot in basketball where there's either a success or a failure. And typically, but definitely not in all cases, in professional basketball, free throws are shot in pairs. And so what we have here on the rows is that we have information regarding Larry Bird's first free throw attempt. Was it a success or failure, or what I call made or missed? And then on the columns, we have information regarding his second free throw attempt. Was it a made or miss? So if we just focus on this 2x2 portion of the table here, what we see is that 251 times Larry Bird made the first, but made the first and then also made the second. 34 times he made the first, but missed the second, and 285 times, outside this 2x2 part, 285 times he made the first free throw. Now, for those of you who may be basketball fans, what kinds of questions would you be maybe interested in answering with this kind of a data? What do you think?
Does the probability of a second make go down if I have a first one?
Exactly. I'm a basketball fan, and when I watch some of these games, I see that a player missed that first free throw. And, I think, well, maybe he's going to get really down on himself, psych himself out, and maybe his probability of success will be lower now that he missed that first free throw rather than made. So what we might be interested in doing is looking to see, well, is there an association between what happens on the first free throw versus the second free throw? And so that's something that we'll be looking at. Another more recent example deals with HIV vaccine clinical trials. So you may remember hearing about a few years ago the first clinical trial where it was shown that a vaccine had some effect in preventing HIV infection. This made national news. It was all over the place. The corresponding paper was published in the New England Journal of Medicine. And here's the data that they use, or primarily the primary set of data that they use to make their judgment about the vaccine and its effectiveness. And so on the rows we have information about the treatment that was applied. Was it a vaccine or was it a placebo? And then on the columns we have a response. Did a person after a few months come down with HIV or did they not? So in total, for example, 8,197 people were given the vaccine, where after a few months, 51 of them still came down or became infected with HIV. So again, in this kind of a setting, what we like to be able to do is compare the probability of getting an HIV infection for the vaccine group versus the placebo group. And we will be looking at that again shortly. Excuse me. So, what we're going to be working with again is that we have a binary response. And just to make things easy here, let's just call the two response categories that we have as success or failure. And we are going to have two probabilities of success that we want to compare. We will denote those as pi 1 and pi 2. So pi 1 could be the probability of Larry Bird making that second free throw attempt, given that he made the first. Pi 2 would be the probability that he makes that second free throw attempt, given that he missed the first. And we can summarize this in a nice table-like structure. So again, here's our responses: success, failure. We observe, in a general sense, information over two different groups, Group 1 and Group 2, and we're really interested in comparing pi 1 to pi 2. Of course, the probability of a failure would be 1 minus pi 1 or 1 minus pi 2, and if you add those up, you always get 1, of course. Now, to make this kind of a comparison, what we're going to do is be observing some binary responses. We can summarize these binary responses then into, let's say, a binomial count. So to put a probability structure or a stochastic structure on this, we're going to work with a random variable w sub j. So w is going to be the number of successes for the jth group, w sub j. And it has a binomial distribution with n sub j trials. Pi sub j is the probability of success on each trial. So again, if we wanted to, we can summarize this in a nice table-like structure. So little w1 is our observed number of successes for group 1, and 1 minus w1 is the observed number of failures for group number 1, and again we have n1 total in group 1. Of course, then the maximum likelihood estimate for this probability of success then is the observed proportion of successes. So pi hat sub j is going to be the maximum likelihood estimate for pi sub j, and it's simply going to be w sub j divided by n sub j. Now, maximum likelihood estimators have some very nice properties that we will take advantage of here today. And this is for large samples. And maximum likelihood estimators have an approximate normal distribution. The estimators are consistent, meaning that for a large enough sample size, you're going to get to where you want to be in terms of estimating your parameter. And we have a convenient way to estimate then the variance of maximum likelihood estimators based upon the second derivative of a log likelihood function. So applied to this particular situation then, pi hat sub j has an approximate normal distribution with a mean of pi sub j and an estimated variance of pi hat sub j of pi hat sub j times 1 minus pi hat sub j divided by n sub j. That's going to be useful for coming up with distributions later for other statistics. Okay. So again, as I was mentioning before, we want to do some comparisons for pi 1 and pi 2. Well, how can you compare the two? Well, you could just simply take the difference in the probabilities, pi 1 minus pi 2, and of course it might be of interest then to determine, well, is it equal to 0 or not? Because if it was equal to 0, the two probabilities of success would be the same. But you could also use something called the relative risk, which instead of taking the difference between the two probabilities, you're actually taking the ratio, pi 1 divided by pi 2. And if this was equal to 1, again, that would say then that the probabilities were exactly the same. And lastly, one could look at what are called odds ratios, where simply you just rescale the probabilities into odds and look at let's say the odds for group 1 divided by the odds for group 2. And again, we might be interested in, is that equal to 1 or not? If it was equal to 1, then that also means that pi 1 is equal to pi 2. So we are going to focus on these odds ratios. Originally in our first draft of these slides, we also were talking about differences in probabilities and relative risk, but to save time, we decided to take that out. But those are some of the extra slides that are available on the course website. We decided to focus again on odds ratios because they appear all over categorical data analysis. They're going to be a very useful tool to use when we are using regression models and understanding the relationships between an explanatory variable or covariate or independent variable with the response. Okay, so let's talk about these odds ratios. So, an odds of a success. First of all, let's begin with. And all that is simply a rescaling of a probability. That's it. And it's just simply the probability of success divided by the probability of a failure. Or if we generically denote a probability of success by pi, it's just pi divided by 1 minus pi. That's it. Probabilities of success, of course, or any kind of probability, will be between 0 and 1. Odds are between 0 and infinity. So if we had pi equal to 0.1, then the odds of success would be 0.1 divided by 0.9 or 1/9. That's all. Now again, we're going to be interested in computing multiple odds of success, one for group 1, one for group 2. And so we can then just simply denote the odds of success for group 1 as odds 1, odds of success for group 2 as odds 2. And then that leads then into this comparison. So we're going to let an odds ratio generically be denoted by OR. And we just simply take the ratio. Odds of success for group 1 divided by odds of success for group 2. We have put it in terms of the pi, so you have some nice simplifications. You have that probability of success for group 1 times the probability of failure for group 2. All that divided by the probability of success for group 2 times the probability of a failure for group 1. Now let's talk about the interpretation. This is a very common place where I see students who are, let's say, just beginning to understand what odds ratios are, misunderstand what an odds ratio represents. Also, unfortunately, you often see in the media, reporters and stuff, when they're writing articles about various things, also misunderstand what an odds ratio is representing. Very often you'll see them interpreted as probabilities. But here's just some standard interpretations. And I think one of the reasons why odds ratios are somewhat confusing at times is that there's more than one interpretation that can be, or there's more than one way to phrase an interpretation. So here's a standard one that we like to use, and that is the odds of success are OR times as large for group 1 than for group 2. So OR in the end is going to be some number, maybe 5 or 0.5. And again, it all comes down to you're just taking one odds divided by another. And this is just a simple interpretation of that. Now, sometimes, depending upon the actual data application, you would like to look at the odds for group 2 divided by the odds of group 1. And as you might expect then, simply, the odds of success are 1 divided by OR times as large for group 2 than for group 1. So just invert the odds ratio. But where sometimes things become a little bit more, can somewhat get a little bit more complicated, is that let's say instead of an odds of success, you're interested in odds of a failure. So you're just kind of turning things around. You're focusing on that second column, you could say, in that 2x2 contingency table rather than the first one. Well, what's an odds of a failure? Well, it's just simply probability of a failure divided by the probability of success. That's it. And so then if you were to do an odds ratio concerning the two odds of a failure for the two groups, you get then just 1 over the odds ratio that you had previously when you were dealing with odds of success. So that then your interpretation then becomes the odds of a failure are 1 divided by OR times as large for group 1 than for group 2. But again, maybe you want to do group 2 versus group 1, and what you need to do is just invert that 1 over OR so that you have the odds of a failure, or OR times as large, for group 2 than for group 1. We'll have data examples coming up where maybe it's not necessarily as clear what the interpretation is. And we've already mentioned this. Well, what happens if the odds ratio is equal to 1? All that means is that the two odds of success are exactly the same. And so what that means then also in terms of the probabilities, pi 1 is equal to pi 2. And that's going to be important to find out shortly. And lastly, yes?
One stupid question, I guess. Then why do we focus on odds ratio as opposed to relative risk, or just the probability itself?
Well, obviously it depends upon the scenario. Sometimes it is important to focus on probability or relative risk. But as you will see, for example, with logistic regression models, odds ratios naturally occur in that context. And also there are simplifications that occur because you're working with an odds ratio rather than a relative risk. So I recommend stay tuned.
It's historically a mathematically easier parameter to work with.
I guess so.
And that made all the difference.
Yeah, structure. But the thing is, when it comes to application, it's very complicated.
Well, yeah, I think it also depends upon how comfortable you are with working with them, too.
I'm outside of statistics, but the thing is, in order for statistics to be really useful, it's got to be applicable and easy to understand. But I understand it's got to be used in such a way that it's got to be tractable, but it's a little bit too complicated for people, practitioners like me. Not only for us, but also for our clients.
Well, we can get into a long discussion about some of those things. One could say, well, maybe needs to be better statistical training too, at the very basic level. An intro stat course that like a sophomore in college would take, odds are often talked about. So before we get into how we can do the estimation, and then we'll follow up with an example, I just want to mention too that odds ratios can be written in terms of expected counts as well. This is sometimes a way that odds ratios are presented. So again, this W sub j is the count for group J, the number of successes for group J. And so that's a binomial count, and so the expected count would be number of trials times the probability of success on each trial. So n sub j times pi sub j. Then the expected number of failures would be then just n sub j times 1 minus pi sub j. And if you go through some math, one can actually show that the odds can be represented in terms of these expected counts. This will come up a little bit later when Tom does some stuff in section 5. Okay, so let's talk about how we can estimate an odds ratio then. So the maximum likelihood estimate for an odds ratio comes back to, well, what did we have for maximum likelihood estimates for pi 1 and pi 2? And if you're familiar with the invariance property of MLEs, what we can do is we can apply that here by just simply putting hats on top of where we had parameters. So we just stick our MLEs in the expression for the odds ratio itself. We then rewrite the expression in terms of the W's and the N's, and this is what we get in the end. And what this comes down to then is that you're basically looking at your table and you're taking the product of the stuff that's on, you could say, the diagonal of the table, W1 times N2 minus W2. So in other words, the number of successes for group 1 times the number of failures for group 2. And you're dividing it by the stuff that's on the off diagonal. The number of successes for group 2 times the number of failures for group 1. That's your maximum likelihood estimate. Now, there can be a problem that occurs, and that is, suppose, for example, W2 is equal to 0. Well, good luck in calculating that. And so there's a variety of options of what you can do. For example, what we typically do is simply add 0.5, or you could do some other small count too, to all the cells of the contingency table. And then you can go ahead and calculate it. What that ends up doing is making that odds ratio, you could say, a little bit closer to 1. So to some respect, it is a more conservative approach, because the closer you are to the 1, the less association there is between the rows and the columns. In terms of then doing inference, we can apply to basic maximum likelihood estimator results, and we can use a walled confidence interval. And the basic form of a walled confidence interval is simply you take your estimator plus or minus a value from your standard normal distribution times the square root to the estimated variance of your estimator. And this just comes about through using the large sample normality of any most maximum likelihood estimators. And one could do that then with your estimated odds ratio. But it turns out that you working with the log of that estimated odds ratio, you get a better normal distribution approximation. And so that's why you will see most people work with the log and then eventually transform back to original odds ratio scale, you could say. Now, the estimated variance then for the log of that estimated odds ratio can be derived through using a delta method approximation. And in the end, it becomes just simply the reciprocal of the counts in the contingency table all added up. Of course, you might worry about having a cell count equal to 0, and you can do the same kind of fix that we just talked about, or that I just talked about a minute ago. So that then an interval for the log odds ratio comes about through using the estimator. So the log of the estimated odds ratio plus or minus that value from the normal times the square root of the estimated variance of the estimator. To get this back to an odds ratio numerical scale, well, just apply the exponential function. Okay, finally, let's go ahead and talk about an example. So this is going to get us back to the HIV vaccine example, and we'll see why the conclusions by the authors of a paper and then also by what was presented in the media were that there was that this vaccine actually has some effect. So in R itself, to do a contingency table, you can use the array function. And the first argument of the array function is data. What's in your contingency table. And so what I'm going to do is I'm going to combine together a vector of my counts. So the first thing I'm going to do is I'm going to put in column number 1 and then column number 2. You need to put everything in that order to get everything in the right place. Then the dimension of the contingency table I'm going to combine together the number of rows and the number of columns. And the last argument is a little bit more complicated. Dim name stands for dimension names. In terms of, well, what do you call the rows? What do you call the columns? And we take advantage of what's called a list type object in R to put all these names together. So the rows are shown first. That's my treatment, vaccine and placebo. And the response, or the columns, are shown second. So I put this all into an object called C.table for the lack of a better name. C.table standing for contingency table. I type C.table in my command prompt, and I get my contingency table back. Now, since this is an array, you can actually access rows, columns, as you kind of might expect. So if I say C.table bracket 1, 1, and I'm just making this be a mess there. Sometimes I write too much. 1, 1, row 1, column 1, I get back my row 1, column 1 count. If you wanted to, you could actually just do this with a whole row or even a whole column. So if I leave off the column designation, I get the whole row. Note that this is one place where I have a little bit in blue there because the bottom there wasn't needed, and the first blue there I actually made a typo. Okay, so now let's look at how we can estimate that odds ratio. Well, it comes back to what is the equation for it. Well, I need that the number of successes for group 1, which is W1, times the number of failures for group 2. So I just pull that out of my C.table object. I divide it by then the number of successes for group 2 times the number of failures for group 1. And I get a 0.69. Now remember what we're doing here with this odds ratio. It is the odds, you say the estimated odds for group 1, the estimated odds for group 2, where group 1 is the vaccine group. Group 2 is the placebo group. So what this is saying is that the placebo group has a higher odds of coming down with HIV than the vaccine group, at least in this sample. So that's a good sign. Now to do formal inference then, well, how about we do a 95% confidence interval? So I create an object alpha, set it to 0.05. I find my estimated variance of the log odds ratio by just, again, transforming the formula that we saw before into the correct syntax. Then to find then the confidence interval itself, what I do is I take my estimator, the log OR dot hat, plus the value from the standard normal. This actually is going to give me two different ones, 1.96 and positive 1.96. I'm actually doing the calculation simultaneously using this Q-norm function by asking for both the alpha divided by 2 and the 1 minus alpha divided by 2 quantile. And because how R does its calculations using vectors, everything's going to be everything's going to be done correctly. Then I'm going to multiply that by the square root of that estimated variance of log of the OR hat that we just did. And here's my interval, 0.48 to 0.98 after I round to 2 decimal places to make it look nice. So notice that 1 is not in the interval. This is why the authors of the paper concluded that there was evidence that this vaccine is working. I personally think that they made a little bit too strong of a conclusion there because we can see that 1 is obviously very close to that upper bound. But it helps when 1 is not in that upper bound because then you can have the media, you can tell the results to the media and the media can make a big deal about it. Unfortunately, I think since then they have not been able to replicate the effect in other trials, if I remember correctly. So a formal conclusion then is that with 95% confidence, the odds of contracting HIV are between 0.48 and 0.98 times as large for the vaccine group than for the placebo group. So in this particular case, we're coming down with HIV as a success, and the vaccine group is group number 1, the placebo group is group number 2. Now, as I said, there's many different ways to do the interpretation. This is just a standard way. Another way to do this is to say, well, the vaccine reduces the odds of HIV infection by 2% to 52%. Where did I come up with that? Well, that 2% is 1 minus 0.98. The 52% is 1 minus 0.48. And there's yes?
Did the authors publish
Yes.
a 95% confidence interval for something like a vaccine?
I believe they actually published what's called a Pearson chi-square test instead. I believe that's what they did for their paper.
Thank you.
We have a number of exercises in our book that talk about this specific example, because there's actually different versions of the data than that they actually publish in the paper, where some of the other versions don't come up with the same kind of significant conclusion. Anyway, it's a whole interesting thing about what happened. So, again, there's other interpretations. So, again, if we think of coming down with HIV as a success, the odds of contracting HIV are between 1.0 and 2.08 times as large for the placebo group, which would be group 2, than for the vaccine group, group 1. So all I did was I inverted. I took 1 over 0.98 and I got 1.02. 1 over 0.48, I got 2.08. And lastly, maybe this might be a more interesting, a better way to phrase this. The odds of being HIV-free, which would be our failure group, our failure response, going back to originally how we defined everything, are between 1.02 and 2.08 times as large for the vaccine group, which is group 1, than for the placebo group, which is group 2. Often when I teach this corresponding course to my students at the University of Nebraska, I often will put a test question where I ask them, come up with 8 different ways to interpret the odds ratio, just for practice. Okay, so there are other ways to perform these calculations. You know, what I did is I like to say is I gave you like the by hand way to do some of these calculations where we actually program the formulas into R. There are more automated ways to do this. Both one from the EPI package and one from the EPI tools package. These are user contributed packages. And, you know, when Tom and I decided to write the book, we at the very beginning decided to focus on the stuff in R that's already there by default, rather than rely on user-contributed packages if we didn't have to. And so with some of these simple calculations, such as an odds ratio, that's why we decided to show you the by-hand way rather than the more automated ways as here. But there's another reason, too, and that is, you know, these are user-contributed packages, and unfortunately they are open to let's say, errors more often than ones that are already automatically installed by default. And in fact, when we were putting together this continuing education course at the beginning, I was doing some stuff with the EPI package, or at least I was trying to include some slides for the EPI package, and the EPI package was no longer available from the R website when I was trying to do this. And I couldn't figure out what's going on. I've used this EPI package many times before, but it was actually removed temporarily from the Comprehensive R Archive Network, or CRAN, for a while. And that just shows you that you got to be careful that if you're doing stuff that's relying on user-contributed packages, you know, packages can be removed. And we found this a number of times when writing the book. There can be errors in some of the functions. It doesn't happen often, so I don't want to worry you too much, but it can happen. Okay. Yeah.
Is it a greater worry that it might not work with a particular version of R?
Well, I would say, the newer your version, the less worry there is, but also in terms of packages too. If a package is uploaded in version 0.1 and has not been updated for a few years, I might be more worried than, let's say, version 2.5 that's been continuously updated over the years. And so that's what I use for my own judgment. I also look at the author of the package. If I'm familiar with them, if I'm familiar with their work, maybe they've written a textbook. I'd be more willing to trust that than somebody who I don't know. Sometimes what you run into is that these PhD students will write a package corresponding to their dissertation, and then once they graduate, they just kind of forget about that package and don't worry about it anymore. Unfortunately, that can happen. But even with other software packages, there are errors in those packages too. So just because it's user contributed doesn't mean it's it's not necessarily worse than like a SAS or something else. Okay. Any other questions before we move on here? I just want to check to see how I'm doing in terms of time here. Okay. I'm 5 minutes over. Let's talk about analyzing a binary response now with logistic regression. So we got this basic situation out of the way. It's going to set us up for using odds ratios then with logistic regression, because that's the primary way that people interpret the relationship between an explanatory variable and the response. Okay. First, let's just simply review a little bit a linear regression model. So, in the very basic setup, we have a response y. We're going to be looking at the expected value of it, and we're going to be related to a linear combination of regression parameters denoted by the betas and explanatory variables, or people might call covariates or independent variables denoted by the x's. Typically, we assume that the y is distributed independent normal with a mean equal to that expected value that we just had there, and a constant variance for every single observation. So variance sigma squared. But in our situation, though, we're going to have y as a binary response. You can think of it as a Bernoulli response. It has a probability of success parameter that's going to be denoted by pi sub I. And the expected value of y, of course, then is pi sub I as well. So we have some problems then if we wanted to use the standard old, the standard old setting here. Y doesn't have a normal distribution. So if you're analyzing binary data, assuming it has a normal distribution, guess what? Things aren't going to always work out as you would expect. Also, for a Bernoulli random variable, let's say the variance of y sub I is equal to pi sub I times 1 minus pi sub I. And so you could have different variances for every single observation, and that violates the constant variance assumption. And then lastly, this linear combination of the betas and the x's is not constrained to be between 0 and 1. But in our case, we're interested in the expected value of y, which is pi, the probability of success. We need a probability of success to be between 0 and 1. So what's done instead then is use a logistic regression model. Now, there are other types of binary regression models out there, but this is by far the most used, and you'll see why it is later on. And so this expected value of y is equal to pi sub I is equal to now this transformation of this regression parameter, of this linear combination of regression parameters with our explanatory variable, taking advantage of the exponential function. Excuse me. Notice that numerator cannot be greater than the denominator. Also, the exponential function, of course, is always positive. So we have something that's constrained between 0 and 1. So that's great. Also, if we start just from the standpoint of y is distributed Bernoulli and derive everything based upon that, it's okay to have a non-constant variance. Now, this transformation involving the exponential function has the same form as a logistic cumulative distribution function. That's where the name for logistic regression comes from. Not from, we're assuming y has a logistic distribution. It's because of the form of this transformation there. There are equivalent representations, though, of our model. So what we could do is solve so that we just have this linear combination of the betas and the x's, solve so it's just only on the right side. Then what's on the left side then is this log of pi sub I over 1 minus pi sub I. Now hopefully this part right here looks familiar. Does anyone remember what that is? It's the odds of a success. Okay? And so we're working with the log odds of success equating to the linear combination of the betas with the x's. Now this log odds of the success has a specific name to it in terms of a transformation of pi sub I. It's called the logit transformation. So very frequently you will see people instead write this more simply as logit of pi sub I. And if we're all comfortable saying with, yeah, we're working with that ith observation, we could drop the I and just write it more simply. And we could do the same thing if we had just pi on the left-hand side too, without the I. So let's take a look at a plot of what this model would look like then. So in this particular situation, we have beta 0 equal to 1, and on the left-hand side we have beta 1 equal to 0.5. On the x-axis, and we're going to have just one explanatory variable here to make things simple, and so we can graph it easily. We'll have one explanatory variable known as x1, and on the y-axis, we're going to put the probability of success pi. And so the curve that you see there is what this logistic regression model looks like. Some things to note that as x changes, so does the slope of this line. And in fact, the maximum slope occurs right at pi of 0.5. Also, we see somewhat of like a symmetry property of what's above that line at 0.5 versus what's below that line. Notice that the line never goes below 0 and never goes above 1, so that's good. And lastly, beta 1 is 0.5, a positive 0.5. So as you might expect, that means that we have a positive relationship between x and pi. So as x is increasing, pi is increasing. Well, what if though beta 1 was equal to negative 0.5? Then that means we have a negative relationship, as we see in the right-hand side plot. So we need to figure out how to estimate these betas. And what we're going to do is use maximum likelihood estimation. Our y's have a Bernoulli distribution to them. So for maximum likelihood estimation, then what that means is that we simply can take a product of Bernoulli distributions, one for every single observation that we have. A key thing to note is that we have an I on pi here to emphasize that this is where we get the betas from. This is what our model is representing. So I could have, I guess, rewritten it in a lot more messier form where I actually put in the model, but I think this is a lot cleaner representation. And so we want to maximize this likelihood function with respect to the betas. And the way to do that is, it's unfortunate that in most situations you can't necessarily find a nice closed form expression for what the beta maximum likelihood estimates, or what I'm going to call beta hats, are in terms of your x's and the y's. And so what you're going to have to do is use numerical iterative methods to find the beta that maximizes that likelihood function. And typically what's done is you use iteratively reweighted least squares or equivalently Fisher scoring. Now R does this automatically for us using the nice function GLM. But do note that in any kind of numerical iterative method, you do sometimes have to worry about convergence. Meaning, do you truly get to the thing that's going to maximize the function in this case? And there are cases where you do have convergence problems. This now is one of the places where Tom and I decided to cut some information out in order to make sure that we finish on time. But on my website, I talk about the specific case or the main specific case where convergence issues can occur. So you're welcome to take a look at those slides from my website. So our regression parameter estimates, our maximum likelihood estimates, are going to be denoted by beta hats. And just like what we saw in that very simple case with a 2x2 contingency table, we can use appeal to the to maximum likelihood estimation theory, and we can come up with a variance covariance matrix based upon the second partial derivatives of log likelihood functions. So let's go ahead and take a look at an example then. This deals with place kicking in the National Football League. Simply put, in football, points are scored by doing this kick of a football by kicking a ball through a target area. So either you have a success or a failure. Now, just to show you how important this is in football, and for those of you who maybe are not familiar with or do not pay attention to football, I do have a short video here of a place kick. Okay, so this video comes from a playoff game in the NFL, about a year and a half ago, between Seattle and Minnesota. Are there by chance any Minnesota fans here? Good, because I was going to tell you, you can go ahead and walk out the door because you don't want to see this. And so anyway, to give you some background, the score at the very end of the game was Seattle had 10 points, Minnesota had 9 points. But Minnesota had one more chance to get more points than Seattle. They were going to kick a type of place kick called a field goal, which is worth 3 points if successful. Let's see what happens. Let's see if I can turn up the volume.
Take a moment to notice, first of all, that he's not very far away. He has to kick the ball between those yellow posts there in the top. He's not very far away in a grand perspective.
Yeah, we should mention, so, the target area is between those yellow, what are called goalposts. That's where he's trying to kick the ball from. And by the way, the kicker's name is Blair Walsh. Let me go ahead if you want to say something else. I'm going to try to...
At this point, this is a home game for Minnesota, and pretty much everybody in the stadium sees those goalposts, sees where he's standing, and says, "We got this."
There's another volume next to play on the far left.
On the far left? Oh. Yeah? Yeah, I tested a different video before starting here today, and the volume was great. For some reason, the volume here is not as good, but I think you'll still get the same effect from watching this video without necessarily hearing the sound. And you can see the football goes to the left. It's no good. Everyone in Minnesota is kind of depressed right now, and you can see Seattle is extremely happy, and they are pretty much thanking everyone, as you will see, saying a prayer. Okay. So, anyway, there's a place kick. So, Tom and I have been very interested in place kicks for some time now because, unfortunately, our teams often lose due to a place kicker missing a kick like this. And so, a number of years ago, we actually collected some data on place kicks in the NFL, and it was actually from the 1995 season. And we collected a whole bunch of information on every place kick that was attempted. We're going to focus on two of the variables right now. Let me actually make this a little bit bigger, sorry. Our response variable is binary, success or failure, 1 or 0. And it's going to be in a variable called good in the data set. And we're simply right now going to look at one explanatory variable, distance. So we're going to try to relate the distance of the place kick to the probability of success. As you might imagine, the farther you are from that target area, or those goalposts, the harder the place kick is going to be, so you would expect the probability of success to go down. Okay? So with this particular data set then, I'm going to first read it into R, and it's in a comma delimited file, so I just simply use read.csv. I put it into an R, what's called data frame called Placekick. And I look at the first 3 observations, just as kind of a check to make sure everything looks good. And so, for example, the first observation here has a distance of 21 yards, and it was a success. There's a lot of other variables there. We'll talk about a few of those as we go along here today. And to actually estimate the model then, that uses distance to estimate the probability of success, I'm going to use the function GLM that I mentioned before. And I need to tell R, well, what is my model going to look like? So that's where the formula argument comes in. My response, or Y, is good. And then I separate the response from any explanatory variable that I have using a tilde. And so my explanatory variable is distance. If I were to have, let's say, other explanatory variables, maybe a variable called W, all I would do is do plus W there. Plus means and, doesn't mean that you're actually adding X and W together. Then to say that I want a logistic regression model, I use the argument family. And remember, we have a Bernoulli response. Of course, a Bernoulli is a special case of a binomial. So I say binomial. This is just the syntax. And then how am I linking then pi, or the expected value of y, to my linear combination of the regression parameters and explanatory variables? I'm using that logit transformation. My data is in Placekick. Then I put all the results from GLM in an object called mod.fit for the lack of a better name. Mod.fit means model fit. Now, mod.fit has a lot of good information in it. And to see the information, I can use the names function R. So, for example, there's one part right here called coefficients. And this gives me my beta hats. So, beta hat 0 and beta hat 1. And if I want to then, I can, eventually, I'll just skip ahead here. I can write out the model then. Here's my beta hat 0. Here's my beta hat 1. Sorry for my poor handwriting. So logit of pi hat is equal to 5.81 minus 0.115 times distance. Notice that that is a negative coefficient on distance. So as distance increases, the probability of success goes down, as you would expect. We'll see some nice plots of that later. Excuse me. Okay. As we saw, there's a lot of information that's inside of mod.fit. So why don't we summarize that information using a function R called summary. So I say summary mod.fit. And this is what we get. So if I look in the coefficients table, estimate column, notice what the rows are called, intercept and distance. Here is my beta hat 0. Here's my beta hat 1 that we just saw. In the standard error column, we get, for example, the square root of the estimated variance of beta hat 1. So R automatically pulls that out of that variance-covariance matrix. There's a lot of other information there that we'll talk about as we go along here today. One thing I want to mention is that we did have convergence, and it took 6 iterations to do it. Okay, so the estimated variance-covariance matrix, if you wanted to see that whole thing, you can use the function called vcov in R with your mod.fit, and it does the calculation for the whole matrix. So the 6.954 times 10 to the negative fifth is your estimated variance of beta hat 1. Let me just make sure I wrote something correctly on this slide. Yeah, so before I had pointed out the square root of the estimated variance. So if you square 0.00834, you of course get the variance. Okay. Now let's go into doing some hypothesis tests concerning our logistic regression model. We're going to start with, first of all, a model that has, let's say, 2 explanatory variables in it, and then we'll come back to the place-kicking data example. So we have 2 explanatory variables, and let's say that I'm really interested in that second explanatory variable. I want to determine, well, is there really sufficient evidence to say that that variable is important given that x1 is already in the model. So anyway, can't talk now. Let's do a hypothesis test for beta 2 is equal to 0 versus beta 2 does not equal 0. And what that equivalently then can be represented is in HO you have a model without x2 in it, and in HA you have the model with x2 in it. And the way that we can do this hypothesis test, or the best way to do it, is to use a likelihood ratio test. Simply put, the likelihood ratio statistic itself is the maximum possible value that your likelihood function can take on if this model with just x1 in it was correct. The denominator is the maximum of the possible of the likelihood function, assuming either HO or HA is correct. And that ends up being, basically, you're working with this alternative hypothesis model. So we saw the likelihood function before. Just you could say you could actually do this. You could actually estimate both of these models, get your pi hats for every single observation, put it into the likelihood function, and do this calculation to get lambda. Now, -2 log lambda has an approximate chi-square distribution to it. In this particular case, I only have one parameter that I'm testing, so in this particular case, it's a chi-square 1 distribution. If instead that I had more than one beta that I was testing, well, let's say q betas, then that's what the degrees of freedom would be for that chi-square distribution. And this has an approximate chi-square distribution for a large sample. And so what that means then for us is that we would reject the null hypothesis if -2 log lambda is large relative to that chi-square 1 distribution. And as I said before, if you're testing q regression parameters, use a chi-square q distribution instead. Now, another way that you could do this test is using walled tests. Likelihood ratio tests are better, so that's why I am using that here. And what I just mean is that the test statistic is better approximated by the chi-square distribution for smaller sample sizes than a walled statistic, if you're familiar with a walled statistic. Okay, so let's go back to the Placekicking data set and see how we can do this in R. Now, another variable in the data set is called change. It's a binary variable, explanatory variable, denoting lead change versus non-lead change place kicks. So, for example, in that game between Seattle and Minnesota, the score was 10-9. If successful, that place kick, which was a field goal, would give Minnesota 3 points. And so the score would be 12-10. Minnesota would in fact, would actually win, since it was the end of the game. But it would cause a lead change, because Minnesota would be leading if successful. If instead the score was, let's say, 10-8, that would be a lead change place kick. If the score was 10-10, that would be a lead change place kick. If the score was 10-7, that would be a lead change place kick. If, however, the score was 10-6, that would not be a lead change place kick, because if successful, the score would be 10-9. So why do you think change might be a variable to look at in the context of place kicking, for those of you who are football fans? Pressure? Yeah. So, how do you measure pressure? You can't go up to the place kicker and say, right before he does the place kick, are you feeling pressure? We couldn't do that. We didn't have the research funds, I guess, to do that. And so, you have to look at other ways to do it. And one of the ways that we investigated was this change variable as a pseudo way to measure pressure. So let's go ahead and estimate the model with both distance and change in it, and then we'll do a hypothesis test to determine if there is actually a significant change effect. So to estimate the model, here's my response, good. My two explanatory variables, change and distance, and I separate them by a plus sign. I put all the results into mod.fit2, for lack of a better name. I summarize everything, and so here's my beta hat 0, the beta hat 1 then for change, and the beta hat 2 for distance. So this is the hypothesis test that I'm interested in. The HO model has distance in it. The HA model has both change and distance in it. So in other words, I'm testing, is this beta equal to 0 or not? There are two main ways to do this hypothesis, to get the necessary statistics to do the hypothesis test in R. One is called the ANOVA function. Now you might be saying, wait a second, we're not doing analysis of variance here, we're doing logistic regression. Yeah, that's right. It's just a lot of the same kinds of questions that you'd be interested in a standard analysis of variance can be done here in terms of testing particular factors or explanatory variables, and so that's why the ANOVA function is used. Yes?
Is the coefficients correct in your null hypo? You want beta 1 distance, and then the second one you want beta 1.
Yeah, perhaps I over simplified that. The betas here are not necessarily the same. It was just a nice way to be able to write out the model simply. So, yeah, thank you for pointing that out. They're not meant to be the same. Okay. So now, excuse me. To do this test then in R using the ANOVA function, I need to have both the null hypothesis model and the alternative hypothesis model estimated. So if you remember, the null hypothesis model we've already estimated, and we put the results into mod.fit. And then using the ANOVA function, I can just put in my null hypothesis model, or HO model. And then I can put in my HA model, alternative hypothesis model. And I say, well, what kind of test do I want done? Well, I want to likelihood ratio tests. Remember, we use a chi-square distribution approximation with that negative 2 log lambda. So the syntax is test equal chi-sq. And this is what we get then. The key thing to look at is this deviance column. This is your negative 2 log lambda. The p-value is 0.022 using a chi-square win approximation. So what we have here is, I would say, not necessarily strong evidence. We have marginal evidence that, given that distance is in that model, change is important. But again, it's not strong evidence. Now, there's some other stuff that's listed in the table. In particular, this resid.div, which stands for residual deviance. And what the residual deviance is a special kind of negative 2 log lambda statistic that always tests a model of interest versus a saturated model. And what a saturated model is basically the largest possible model that you could have. Meaning that if you have, let's say, 1,000 observations, you have 1,000 parameters. And what it's going to end up doing is giving you a perfect fit to the model. And so what this 776 is actually a residual deviance for this model compared to a saturated model. This 770 is the residual deviance, or a negative 2 log lambda statistic, comparing that model to a saturated model. And in fact, if you wanted to, you could actually pull out those residual deviances from the corresponding places where we save the model fit information. Now, the reason why then R actually prints that information out is because if you were to subtract those two residual deviances, you get the 5.25 that we get for the test that we want. And one could just simply mathematically show, actually for any hypothesis test like this, you can do the algebra, that this will always happen when you subtract those two residual deviances. So I just wanted to point that out so you have a better idea of, well, what's being actually displayed in that table. Now there's another way then to do this hypothesis test that's a little bit easier in R, and that is to use the ANOVA function. Anybody's saying, wait a second, you just use the ANOVA function. Well, it's a different ANOVA function. Notice that this has a capital A there, where in the previous slide we had a lowercase a. R is case sensitive. This and I like to call this capital ANOVA function or big ANOVA function to differentiate it from the little ANOVA function. This ANOVA function comes from the CAR package. This is a user-contributed package. CAR stands for Companion to Applied Regression. There's actually a book that was first written in about 2001 or 2002. It's one of the first books on R out there. And this provides a nice way to do the test that we're interested in. And so I need to first install the package, and then once I install it, I can say library CAR to say, hey R, I want to use the functions that are in that package. And then simply with ANOVA, for the mod, for model option, or argument I should say, all you have to do is put in that alternative hypothesis model, or the results from fitting that alternative hypothesis model. And then, well, what kind of tests are we going to do? Well, in this case, the syntax is LR for likelihood ratio. And so if we take a look at this, for the change row, we get our negative 2 log lambda statistic. Notice there's that same p-value that we had previously. Also what this gives us, though, is a test for distance. So given that changes in the model, is distance important? And we get a 218.6, it's a negative 2 log lambda, and we get a p-value that's less than 2 times 10 to the negative 16th power, meaning that it's extremely small. So yes, distance is important. Now be careful. These two functions don't have the same syntax. And sometimes I see people mix that up. And if you do that, you can actually get a wrong result. I'll let you read this slide on your own, but I do want to point out that if you mix up the syntaxes, you may not get a correct result. Okay, so let's now get back to odds ratios. And we're going to focus on using, first of all, a logistic regression model with just one explanatory variable to make things easy. And remember what we're doing here with a logistic regression model. We are modeling the log odds of success. So this is what our model would look like with one explanatory variable. But how about we turn this into modeling, or rewrite the equation, I should say, so that you have just the odds of success on the left-hand side. So now on the right-hand side, we have the exponential function with beta 0 plus beta 1 times x. That's helpful to know because now we can look at the odds of success for different possible values of x. Maybe x might be the distance of the place kick, for example. So the odds at maybe a general distance, which we'll just call x, I'm going to denote as the odds at x. Then the odds of success for a C unit change in x then is the odds at subscript x plus c. And notice how I put the x plus c in there for where we just had x before. I have two odds. What do we like to do with two odds? Let's compare them. Let's form an odds ratio. And so here's my odds ratio where I have the odds of success at x plus c divided by the odds of success at x. And look what happens here. I have some nice simplifications. The beta zeros disappear. Beta 1 times x disappears. And look what I'm left with. E to the c times beta 1. And what's really, really, really cool is that notice we don't have x in there anymore. So it doesn't matter, relating to the Placekicking example, if you're starting with a distance of 20 yards, 30 yards, 40 yards, or 31 yards, it doesn't matter. X disappears. And the only thing that matters is, well, what is C? What is that change in X? What is a change in distance? This is why people like to use logistic regression, because of this nice little simplification. So then the interpretation, getting back to interpretations of odds ratios, is the odds of success change by e to the c times beta 1 times for every c unit increase in x. Now, if you had other explanatory variables in the model, such as, let's say, change, well, then you would have to add a little bit extra to that interpretation, such as holding the other variables in the model constant. How do I estimate this odds ratio? Well, wherever you see a parameter, put a hat on top of it. So if I put a hat on top of the beta 1, then I get the maximum likelihood estimate for the odds ratio in this logistic regression context. I can then form 1 minus alpha times 100% confidence intervals as well. So a walled interval for a C unit change in X would be, well, let me back up a second here. To do a walled interval, let's go back to basic principles of how you form it. You take the estimator plus or minus the value from your standard normal times the square root of the estimated variance of the estimator. And so to find the confidence interval for the odds ratio itself, what I'm going to do is first find a confidence interval for beta 1. So that would be my estimator, beta hat 1, plus or minus the value from the standard normal, times the square root of the estimated variance of beta hat 1. How about we find a confidence interval for C times beta 1? Well, what's the estimate? C times beta hat 1. So I put the C in there. Using properties of variances, I can factor that little variance out. I'm sorry, factor the C out, I should say. And now, if I want a confidence interval for E raised to the C times beta 1, then I just apply the exponential function to what I just found. We can also find profile likelihood ratio intervals, and typically these work better than walled intervals in terms of its coverage. What I mean by coverage is that when I say that I have a 95% confidence interval, I want it to work 95% of the time. Profile likelihood ratio interval does a better job achieving that than a walled interval. And so, how do I find then a profile likelihood ratio interval? Again, we have this simple model where we only have one explanatory variable. And this is how you find it. So what I want to do is find the set of beta 1 values such that this negative 2 log lambda like quantity is less than a 1 minus alpha quantile from a chi-square 1. So let's take a closer look at what's inside this negative 2 log lambda like quantity. So the denominator is exactly what we've been seeing before with respect to these likelihood ratio tests. It's the likelihood function evaluated at your maximum likelihood estimates, beta hat 0 and beta hat 1. Now, the numerator, though, is as follows. Let's say, for example, beta 1 is equal to 1. If I fix beta 1 to be 1, let's find what the maximum likelihood estimate then would be for beta 0. That's what I denote by beta 0 tilde. Then I evaluate that likelihood function. Find out what the whole value would be. Do negative 2 log of it. And check, is it less than the 1 minus alpha quantile from chi-square 1? So if like alpha was 0.05, this would be 3.84. If then what's on the left side is less than that quantile from the chi-square, that means that beta 1 equal to 1 has to be inside my interval. And I could keep on going. Maybe try 1.1. Do exactly the same thing. Try 1.2. Do exactly the same thing. So as you can see here, I'm basically doing like a numerical iterative method here. And I'm going to look for all values of beta 1 such that this inequality is satisfied. Once I get that, I'm going to have a lower bound and an upper bound for beta 1. If I have an interval for beta 1, well, we can do like what we just did with that walled interval. I can take C times that lower and upper bound and then apply the exponential function, and that's how I get my profile likelihood ratio interval for the odds ratio itself. Again, numerical iterative methods need to be used. Okay, so let's go back to the Placekicking data example. And we're just going to simply work with the model that has just distance in it, just to make these a little bit easier. And let's say that C is equal to 1. So what that means is, for football fans, a 1 yard increase in the distance. Well, then the estimated odds of a success then change by e to the 1 times that beta hat 1, or in other words, 0.89 times for every 1 yard increase in the distance. That's a very, very, very simple interpretation. Now, if you were to give this information to a football coach, they would look at you strangely because they would be wondering, who cares about a 1 yard increase in distance? And so this is a great example of, well, you're the one who chooses that C, and you have to think of a C that makes sense in the context of the problem. So for football fans, we often think of in terms of 10 yards, because 10 yards gives us a first down. So how about we look at C equal to negative 10? So a 10-yard decrease in the distance. Then the estimated odds of success change by e to the negative 10 times beta hat 1, or 3.16 times for every 10-yard decrease in the distance. So what this is telling me is my odds of success are going up if I get maybe that extra first down, or if I get that extra 10 yards, I get 10 yards closer to those goalposts. Let's look at a confidence interval. Now, to do a profile likelihood ratio interval in R, there are two main ways. The first way is the simplest, but it only works in simpler problems. I can use a function called confident. That makes sense. Confidence interval. And for the first argument in confident, I have to specify, well, where's my model fit information? Remember, we saved it in mod.fit. Then what parameter am I interested in doing a confidence interval for? And by specifying distance there, that will allow me to get a confidence interval for beta 1 first. What level do I want to do that interval at? 95%. So then my interval for beta 1 is negative 0.13 to negative 0.099. Notice that 0 is not included in that interval. Then to find a confidence interval for the odds ratio, remember I want e to the negative 10 times beta 1. What I can do is take negative 10 times my information that's in beta.ci. Sorry, I forgot to mention that. That's where I stored my interval. Apply the exp function with it. And then I use the rev function for reverse. Because by using that negative there, what that's going to do is put 3.7 first and 2.69 second. And I want to reverse it so that I have the lower number first, upper number second. And so that my interval is 2.69, 3.74. There's some annoying labels that come along with this. So if I use the as.numeric function in R, that's one way that you can just strip out those labels. So then the interpretation is, with 95% confidence, the odds of success change by amount between 2.69 and 3.74 times for every 10-yard decrease in the distance of the Placekick. Now, for football fans, we probably knew that, the shorter the Placekick, the higher the odds of success, the higher the probability of success. But what this does, it helps to quantify it. Okay, here's a more general way to do the same calculation. It's more complicated than what would normally be needed for this particular problem, but this is going to help out later when we do have more complicated models, and this will be the only way that we can do some of the calculations. So there's a nice package in R called MC Profile. Yes? Yeah, so this is saying it's obviously helpful to get 10 yards closer.
Okay, so but isn't it harder to hit 50 yards field goal, 50 to 40, rather than if I were 40 to going from 40 to 30, shouldn't the odds increase?
Well, remember we're comparing two odds, and what this is saying is that the odds, the amount of increase between the two odds is constant for every 10-yard increment. That's what that is saying there. And also, something that we haven't talked about yet is that there are other important variables out there as well, and we will take a look at some of those coming up that you should take into account, like wind, for example.
I think you shan't, because
One thing that I didn't show in the video is that also, if you're a football fan, you know that place kickers do not like to kick the ball where the laces are. And in that particular case, the laces were actually right where his foot hit it. And so that might have had an effect as well. Although I don't know exactly if that information would be generally available so that we could actually include it in the model. But that is one possibility. But obviously there would be a pressure effect in that case too. And I do want to mention, so unfortunately I did not include it in the slides, for this particular place kick that we've been talking about, I know I have it here. So that one particular place kick, it had a distance of 29, it's either 29 or 27 yards. Pi hat was 0.9374 with a confidence interval of 0.92 to 0.95. Now, as I write this out, I realize I'm getting ahead of myself because we haven't talked about confidence intervals for pi. We're doing confidence intervals for OR. So this is something to look forward to later. But in this particular case, it was a high probability of success. Okay, so let me go ahead and erase that. So there's this package called MC Profile. It is a user-contributed package, but but in its newer versions, it works quite well. Some of the older versions did not always work well. And what this allows us to do is come up with confidence intervals for complicated linear combinations of your regression parameters. And to do this, we need to be able to write what we're interested in this particular setting in that linear combination context. And this is a very simple setting, so the linear combination is really easy. But this is a good place to begin. So let's define a row vector called k. It has elements of k1 and k2. And we want to be able to apply or multiply k times our vector of our betas, beta 0 and beta 1. And we want to choose coefficients that go into that case such that we get what we're interested in, which would be e to the beta 1. That's our odds ratio for c equal 1. And so if I choose k1 to be 0 and k2 to be 1, obviously then I do get just that beta 1 back. And once we've defined what k is, we can use the MC profile function inside the MC profile package to do all those evaluations that I was talking about earlier of this negative 2 log lambda statistic. So it does all those evaluations that are needed automatically. And then we can apply the confidence function with the results from MC profile to find an interval for k times beta. And then use the exp function along with our C unit change to find our confidence interval for the odds ratio. So that's the background. This is how it works then. So again, I'm going to need to download MC Profile, and then I say library MC Profile to actually use it. Excuse me. Then I can form my then I can form K. So K was a row vector, and what I'm going to do is use the matrix function R to help form it. So I'm going to say matrix, and the data or the information I'm going to put into it, I'm going to combine 0 and 1 together using the C function. 1 row, 2 columns, and we don't need to worry about that by row equal true right now, so I'm just going to cross that out. And then I'm going to apply the MC profile function with the results from where I've stored information about the model's fit from GLM. That's mod.fit. And then the CM argument stands for coefficient matrix. This is where I put in my K. I'm going to put all the results then into linear.combo. Then, using that, I'm going to apply the confint function to it. This is actually a different confint function that exists inside the MC profile package itself. So confint object equal linear.combo, 95% intervals, and I'm going to say adjust equal none. You'll see what adjust means later on. And so that's going to find then my confidence interval for this linear combination that I just formed. It's going to find a confidence interval for beta 1, a 95% profile likelihood ratio interval. Inside then the object that I save, which I call ci.log.or, there's a lot of information. In particular, confint. So if I pull the confint out of ci.log.or and do some other stuff with it, I get the same exact interval that I had before, at 2.69 to 3.74. Now, one could also do a walled interval here. There's a few different ways. And the reason why, even though I told you profile likelihood ratio is better, the reason why I mentioned that you can do a walled interval here is that, as you will see later on with some of the other regression models that we have, there are not easy ways to do profile likelihood ratio intervals. So that's why it's often nice to say, hey, walled intervals are possible even here. And what you can do is use a function called confint.default with mod.fit to do the walled interval. And there's also a function in the MC profile package called wall that will help you do that. Our program does have some examples. Now let's talk about estimating the probability of success. Now, and we're going to begin with just simply one explanatory variable because that's the easiest thing to do at this moment. And here's what our model will look like. And if I put hats on top of the betas and choose a particular X that I'm interested in, maybe a distance of 20 yards for a place kick, then I would get my pi hat out. Of course, though, we want to do inferences with the true value of pi, so we can do a 1 minus alpha times 100% walled interval. And to do that, then, it's easiest, or best, I should say, to actually do an interval for beta 0 plus beta 1 times x first, and then eventually come back to what we need for pi itself. So if I do a walled interval for beta 0 plus beta 1 times x, and again, x could be like a distance of 20 yards, for example. Again, I take my estimate of it, which would be beta hat 0 plus beta hat 1 times x, plus or minus the value from the normal distribution, times the square root of the estimated variance of that estimator. And R will provide us automatic ways to do this calculation. Then once I have that, I can then use this exponential function transformation that we've seen with the logistic regression model before to find then an interval for pi itself. Okay? We can also do profile likelihood ratio intervals, and again, these are better when you can calculate them. And it's through using numerical iterative methods once again. We can go ahead and find the interval for beta 0 plus beta 1 times x, and then use this exponential function set of transformations to get the interval for pi. You can do all this with logistic regression models with more than one explanatory variable, so it just simply extends. Let's take a look at an example. This is with the model with just distance in it. And what I like to be able to do is estimate the probability of success at a distance of 20 yards. There's a few different ways that you can do that. The main way is, first of all, to create a data frame in R, meaning a data set, that has what you want to predict at in terms of your x's. So let's do distance equal 20. If I had, let's say, a distance of 20 and 30, all I do is replace that 20 with, I'm going to combine together 20 and 30. That's all. I put that in an object called predict.data. Then to get the pi hat, I use the predict function. So I'm going to take information from my model's fit, mod.fit, and what do I want to predict at? Well, that's where the new data argument comes into play, and I simply use that data frame that we just created, and I want pi hat out. In other words, I want to estimate the expected value of y. I want to estimate the response essentially. So type equal response is the argument that we need. And so my pi hat is 0.971. So a very high estimated probability of success. Let's look at how we can do this with the MC profile package then. So for my k, remember, I use that to find a linear combination of my betas. Oops. Sorry, can't write. Okay. And I want to find it. I want to find an interval first for beta 0 plus beta 1 times 20. And then I'll use the exponential function transformation to get to what I want in the end. And so I'm going to choose a k2 to be 20. And then you can think of 1 times beta 0 there. So I'm going to choose a k1 equal to 1. I put this all into a matrix, just like what we had before. That's my k. And then it's just a matter of applying the same techniques that we just saw. I first use MC profile. And again, what this is going to do is calculate a whole bunch of negative 2 log lambdas for me. Then from those results, I use the conf function, and that's going to narrow down where the interval limits are. So that in the end, my confidence interval for beta 0 plus beta 1 times 20 is 3.186 to 3.867. Then using the exponential function transformation, I can come up with the interval for pi. So 0.96 to 0.98 about. Okay. So maybe a good place to stop. I think 10:15, is that correct? Mm-hmm. Yeah. Why don't we stop right there and we'll get back going at 10:30.